And that clock is going to be deeply disturbing. We are not, in fact, starting 25 minutes late. I do have another clock. Okay, so that means I need to end there. Okay, so this is the second to last lecture on graph algorithms. And in fact, the second to last lecture on material that will be covered on midterm 2. Unfortunately, this means necessarily going to have to make some difficult choices about what material to include and what not to include. In particular, there's one aspect of algorithms on DAGs that we would have liked to cover in lecture, but there just wasn't time for Etienne to get to it yesterday, which is doing dynamic programming like you will need to do on problem 3 of the homework. So I will let you ask on Piazza and we will try to explain there, or you can come to office hours and we will try to explain there. What exactly do we mean when we say use dynamic programming, given that your input isn't an array, it's a DAG? And the short version is, whenever you see a DAG, apply topological sort. Just don't even think about it, just DAG. Step 1, use topological sort. Then read the rest of the problem. And what the topological sort allows you to do is, more or less by definition, assign a number from 1 to n to each of the vertices so that all the edges go from left to right. And now lots of problems in DAGs then turn into subsequence problems in that array of vertices. And if you start thinking about it that way, dynamic programming becomes pretty natural. I wish I had time to go into this in more detail. I do think the problem in the homework is accessible. You just have to have these two pieces that you put together. We're in the middle of the review phase for the problem on homework 6. We set the deadline fairly generously to get the reviews in to be next Tuesday, but do keep in mind that if you do not submit reviews, you will not get credit for that problem on the homework that you turned in on paper. So your grade will be whatever grade the graders give you times 1 if you do the reviews and times 0 if you don't. Okay, so please remember to get those in. For the next homework, we're going to set the review cycle to be a little bit shorter, because I think a week is a bit, you don't really need a week to do that, and it's better just to get it out of the way and get the feedback back to you faster. So watch the webpage for the announcement for the next CrowdGrader assignment. And finally, because this is the second to last lecture on this graph algorithm stuff, that means, according to the schedule, that we've got a midterm coming up in a couple of weeks. The usual, the same protocol applies as we did for midterm 1. There will not be a lecture the day of the midterm. I will, by coincidence, be in this room. We will not have labs the day before the midterm, but the TAs and undergrad staffers will be, by coincidence, in the discussion rooms. And if there is sufficient demand, we may run an additional review session earlier in the week. Now is the time to let us know that there's demand. Also, now is the time to start letting us know if you might need a conflict. Please, I beg you, do not schedule interviews on the day of the midterm. You've known the midterm is going to be on this date for 2 months. The recruiters who are trying to convince you, no, you really need to come out now, they make commissions. They make money by getting people to the places to interview. That is not your problem. Google will wait for you. Microsoft will wait for you. Facebook will wait for you. You're from Illinois, for God's sake. They will wait. it's just a lot easier for you and for everyone else if you just, try to come to the, don't fly out of town in the middle of an exam. If you really can't avoid it, of course, let me know. But you really, no, the recruiters are lying to you when they say they can't reschedule. Pushback. Okay, so far, what we've seen so far for graph algorithms is, we've seen sort of basic data structures, adjacency lists and adjacency matrices, and there are reasons why we focus on these that have to do with more than just this is what you might be given directly, but you might be able to interpret the data you're given to as a graph as though it were already in one of these data structures rather than having to build it explicitly. Then there's whatever for search. This is you put one of the vertices into a bag, and then as long as the bag isn't empty, you take a vertex out of the bag, and if you haven't seen that vertex before, you pull all its neighbors into the bag. Okay? And whatever for search is good for is basically traversing an entire component of a graph. If you put a little wrapper function around it, you can figure out how many components the graph has. But this is the algorithm that you want to use when you don't care about any particular structure in the spanning tree or that you're building. You just want to know how many components there are. You don't need to specify depth first search. Of course, if you've already got depth first search implemented, it is an implementation of whatever first search. But you don't need to insist on doing things depth first. And then the two sort of special cases of whatever first search that are the easiest to implement and the most useful are breadth first search and depth first search. Breadth first search, you use a queue for the bag, and this allows you to compute shortest paths, meaning minimum number of edge paths from whatever your start vertex is to every other vertex in the same component. And then depth first search, you use a stack for the bag, or you implement the bag implicitly by using recursion. And probably the most important application of depth first search is when you have a directed graph. You want to know whether it has any cycles, and if it doesn't, you want to do this topological sorting. Okay, so topological sort is ultimately just a very careful implementation of depth first search with a small amount of bookkeeping. Okay. And this is by far the most important algorithm to know when you're dealing with directed acyclic graphs. The other two that we're going to talk about today and on Tuesday, minimum spanning trees and shortest paths. Okay. Now, both of these, in some sense, hopefully are at least somewhat review. So how many of you have seen minimum spanning trees before? How many of you have implemented minimum spanning trees before? Okay, I'm going to show you an algorithm that you didn't implement, but you should have, because it's better. And I'm going to also show you sort of a general picture of why various minimum spanning trees algorithms actually work. So this is a good example of a greedy algorithm applied to graphs. So the correctness proof is going to involve an exchange argument. But then, just like whatever for search, there's some design flexibility in how you implement that algorithm. And depending on how you decide to fix that, you either get Kruskal's algorithm or Yarnick's algorithm, which everybody calls Prim's, or Boruvka's algorithm. or other algorithms that are even better. And then the last one, which really I think everybody has seen before, is shortest paths. And of course, you probably immediately are thinking of Dijkstra's algorithm. Dijkstra's algorithm is, again, another example of greedy algorithm for applied to graphs. You can also think of it as a kind of whatever for a search, where you're using a priority queue. But it doesn't always apply. It's not always the best algorithm. And so I'll show you a couple of dynamic programming algorithms that work or are faster than Dijkstra's algorithm in situations where Dijkstra's algorithm is either broken or incredibly slow, depending on whether you look at Wikipedia or you look at my notes. Okay. All right, so let's start here, the minimum spanning trees. So the input to the minimum spanning tree problem, as you probably remember, is an undirected graph, no special start vertices or anything like that, where every edge has some weight attached to it, some number. Okay? A spanning tree of this graph is a tree, meaning a connected graph with no cycles, that spans the graph, meaning it uses every vertex in the graph. Yes?
So minimum, I just want to, it's been a while. Minimum spanning tree in this context would be the,
right, you want to minimize the sum of the edge weights in the tree. So, I mean, for this particular graph, you know, I've already pre-computed it. I'm not doing this by magic. Okay, this is the minimum spanning tree, right? There's lots and lots and lots of spanning trees for this graph. You can compute a spanning tree by picking an arbitrary start vertex and running whatever for search. If you implement the whatever for search exactly the right way, this is the tree you'll get. But in general, you won't get that. Okay, so. Does anybody here speak French? Do you know what that means in French? Maladie sexuellement transmittée. So I'm going to use the words minimum spanning tree, because I don't want to talk. Sexually transmitted disease. Yeah. So I'm going to call them minimum spanning trees rather than abbreviating them. When I say, you know, minimum spanning tree, I mean, so tree, this is a, you know, of G, this is a connected acyclic graph of G that includes every vertex with minimum total weight. Okay, so minimum spanning tree. Okay, so how do you actually compute this thing? Now, again, as usual with English, there's this subtlety when I talk about the minimum spanning tree. If I gave you a graph where every edge had weight 1, then every spanning tree would contain exactly v minus 1 edges, and therefore would have weight exactly v minus 1. And so every spanning tree has minimum total weight among all, you know, all spanning trees have exactly the same weight. And still, I'm going to talk about the minimum spanning tree as if it were unique. You can sort of mentally say, okay, I'm using some arbitrary tie-breaking rule to pick one over any other, or when I say the minimum spanning tree, I really mean a minimum spanning tree. But there's a small change to the input that I can use to actually, formally choose a particular one to be the minimum spanning tree. Ultimately, every algorithm for minimum spanning trees is going to boil down to a bunch of comparisons between the weights of two edges. Just like every sorting algorithm, let's say most sorting algorithms ultimately boil down to, I need to compare these two elements of the array, quick sort, merge sort, heap sort, insertion sort, selection sort, bubble sort, Tim sort, not radix sort or bucket sort, but most of the classical sorting algorithms that people learn and implement are based on the idea of pairwise comparisons. The same is true for algorithms that compute minimum spanning trees. And just like for sorting, as long as you have a consistent method for breaking ties, you can assume without loss of generality that the keys that you're sorting are all different. As long as whenever you see two things that happen to have the same value, you have some consistent way of deciding, okay, I'm going to pretend this one is smaller. And when I say consistent, I mean if later in the algorithm you look at the same pair of keys, you get the same result, even if the keys have moved. So the same thing is true here. If I establish a tie-breaking rule, here in this, 5 lines of code or 6 lines of code, this is going to be enough to guarantee that the minimum spanning tree is actually unique. I'm not going to prove that to you here. I just want to mention this in case you ever need to implement something like this. The idea is every edge is going to be specified by 2 vertices, and every vertex is going to be specified in my adjacency list data structure by an integer, an index into the vertex array. So when I ask, is this edge shorter than that edge, the way that I'm actually going to be given the input is I'm going to be given 4 integers between 1 and n. Each represent the first 2 representing the endpoints of edge 1, and the second 2 representing the endpoints of edge 2. Now, in the algorithm, if the actual edge weights are different, I'll return the correct edge as the one that's shorter. Right? So I assume there's some way of looking up the weight of an edge. Maybe these are really pointers into an adjacency list. Maybe these are indices into an adjacency matrix. I'll assume, because it's reasonable in the context of the algorithms, that I can figure out that weight in constant time. But if the weights are actually equal, then I'm going to break ties by actually looking at the indices themselves. So basically, I'll look at the smaller, I'll imagine that each of these edges starts at the smaller index vertex node and ends at the larger index node. And then I compare those 2 pairs lexicographically. Right? The only way that you could possibly end up with a tie with this algorithm is actually if you're passing the same edge twice. That I is equal to k and j is equal to l. And the algorithms I'm going to show you just don't do that. Okay? So I'm going to imagine implicitly whenever I see a tie between 2 edges, I'm going to break it this way, and that's enough to guarantee that, in fact, the minimum spanning tree is unique, even if all of the edge weights are 1. There's a particular spanning tree that tie-breaking rule will choose. Okay, so how do you compute this thing? Well, there's dozens and dozens of different algorithms to do this, except they're all instances of exactly the same general strategy. Okay? So the general strategy is the following. I'm going to grow a spanning forest F. Okay, so the difference between a spanning tree and a spanning forest is that the forest might not be connected. It's still spanning, so it still includes every vertex in the graph, but it isn't, and it's still acyclic. It still doesn't have any cycles because every component of a forest is a tree. But it's not necessarily going to be connected. In fact, at the beginning, I'm going to start by giving the forest, all the vertices but no edges. So at the very beginning of the algorithm, my forest is just a collection of independent nodes. There are no edges at all. Okay? Now, I'm going to say that an edge is safe for some component of f if, let's say, call this edge E, if E is the lightest edge, meaning the edge with minimum weight, with one endpoint in F. Okay? So for every component of my forest, and when I'm in the middle of the algorithm, there'll be some edges that have one endpoint in that component and another endpoint in a different component. Okay? So for each component, I pick out the lightest edge that leaves that component for somewhere else. Okay? And then I say the lightest because I have this tie-breaking rule. Okay, that edge is safe. An edge is useless if both ends in the same component of F. Okay, so now the general strategy is going to be one of the following. Okay, so I start by setting F to be nothing, and then while F is not connected, either add a safe edge to F or delete a useless edge from G. And at the end, return F. That is every minimum spanning tree algorithm. Okay? So let me show you an example using this graph here. Okay, so I'm going to draw the forest. No, forests are green. What am I doing? I'm going to draw the forest here in green. And originally, I'm going to start off with the forest just consisting of these 7 vertices and no edges at all. Okay? There are no useless edges currently, because every edge joins 2 different components. The edge with weight 18 on the far left, this is not a safe edge, because the component at the top has a lighter edge leaving it, and the component at the bottom has a lighter edge leaving it. But this edge labeled 4 is safe, because it's the lightest edge leaving one of its endpoints. In fact, it's safe for both of those endpoints. So I can add it to F. Now, still no useless edges. But now this edge here labeled 12 is safe because it's the lightest edge leaving this component down here in the bottom right, or bottom left. Okay? There are 4 edges with one endpoint in this component, 18, 12, 14, 26. 12 is the lightest one, so it's safe, so I can add it to the tree. This edge up here, 5, it's safe because it's the lightest edge leaving the top endpoint, so I can add it to the tree. To the forest. Now this edge labeled 14, it has both endpoints in the same component of F. So it's useless, I can throw it away. Right? And if I just sort of wander around at random, say, oh, okay, what's the safe edge leaving this one? Oh, it's 16. Okay, good. Are there any useless edges? I don't think so. What's the safe edge leaving this component. I think it's this. Okay, now suddenly this is useless and this is useless. And now what's the safe edge leaving that? It's 2. Hey, look, the graph, the forest is connected and I'm done. Okay? That's the generic minimum spanning tree algorithm, and if sure enough, I got the same tree. Okay. All right, so is everybody clear on what these two adjectives mean, safe and useless? Okay. Yes? G is the input graph. G is the graph whose minimum spanning tree I want to compute. Okay? Nodes do not have height or weight. So safe means, let me draw a somewhat more generic picture here. All right, so in the middle of the algorithm, I've built up a forest, which is going to consist of several trees, and say for this component of f, I might have several edges that leave it for other components. Out of all those edges, with one endpoint in this component, the one with minimum weight is safe for that component. No. Right. In fact, if you remember when I went through this example, I added this edge 12. This was the second edge I added because it was safe for this component down here. But it wasn't safe for this node here in the middle, because there are other edges coming out that are smaller. Okay, so the edge doesn't have to be safe in both directions. It can just be safe from one end. All right. So I claim that this algorithm always gives me the minimum spanning tree. I mean, this is a rather powerful statement because I'm not actually saying how you find the safe edges. I'm not going to describe yet how you check whether an edge is safe or how you check whether an edge is useless. Let's imagine that I have a safe fairy and a useless fairy that sit on my shoulder, and I point at an edge, and one of them might say yes. Okay, hey, show me a safe edge. Okay, that one. Okay, I add it. Okay, and then just assume that that when I point at an edge and say, is it safe, that somebody will tell me correctly yes or no. So how do I actually prove that in the end, this is the minimum spanning tree? Okay, so I'm going to essentially do this by induction. Right? So the inductive argument is every time I add a safe edge to f, that is an edge of the minimum spanning tree, which means at all times during the execution of my algorithm, f is a subgraph of the minimum spanning tree. And now I have to argue, to make this inductive argument work, I need to prove the following claim. Every safe edge is in the minimum spanning tree. Okay? Now, if I go back to the discussion about dynamic programming and greedy algorithms, you can think of the problem of how do I build the minimum spanning tree as something you could attack in principle with dynamic programming. The way you might think about it is, I need to identify some edges that belong to the minimum spanning tree. And so you could imagine asking the question, is this edge in the MST or not? And either way you get the yes or no answer, you could then recurse if the answer is no, you delete that edge, and now you have a smaller graph. If the answer is yes, you can essentially pull the two endpoints together into one end, and now you have a smaller graph, and you can recurse. And so you could, in principle, turn this into a dynamic programming algorithm. Or another way of saying it is, as I'm building this forest, I'm going to say, well, from this component over here, I know one of these edges has to be in the minimum spanning tree because the minimum spanning tree is connected. But which one? The dynamic programming algorithm would try them all, and for each one, try to recursively finish out the spanning tree, and in the end, check which one has the smallest weight. What I'm claiming here is that without doing the recursion, I can just say that one, the one with minimum weight. This is a greedy algorithm, so I need to actually prove it, and the way I'm going to prove it is using an exchange argument, just like I do for other greedy algorithms. Okay? So, in fact, I'm going to claim something even stronger, which is this claim holds even if f is not part of the minimum spanning tree. Take any forest at all. In fact, take any subset of the vertices. Okay? Pick your favorite subset of the vertices. Right? It could be one of the components of f, but it doesn't have to be. Then the lightest edge leaving S, meaning having one endpoint in and one point out, is in the minimum spanning tree. Okay? That's my claim. So the way I prove this is I say, well, look, there's the word any. So my proof has to start the same way any proof with the word any in it, is it? Bow to my sensei. Let S be an arbitrary subset of the vertices of G, and let E be the lightest edge leaving S. Okay, now I want to claim that E is part of the minimum spanning tree. So the way an exchange argument works is that, well, suppose not. Suppose I look at some other spanning tree that doesn't have E in it. Suppose the greedy choice, there's a better spanning tree that didn't make this greedy choice. Then by exchanging E for something else in that other spanning tree, I can make the spanning tree better. By making it look more greedy, I can make the total weight smaller. Okay. So I'm going to start by saying let T be any spanning tree that omits E. Okay? And then eventually what I need to do is prove that T is not the minimum spanning tree. All right? So if the spanning tree doesn't include E, then it's not the minimum spanning tree. That's the same as if it is the minimum spanning tree, then it includes E. All right? So what I want you to imagine is I have some sort of spanning tree and on top of that I have some subset of the vertices that's not, in any way related to the spanning tree. Maybe it looks like this. Okay, so the orange vertices are the ones in S, and here is E. This is the minimum weight edge that has one orange endpoint and one white endpoint. Right, this is the edge that's missing. This is an edge that's missing from the spanning tree T. Okay, so this is T. And S are these things. Okay, now spanning trees are connected by definition. And so if I look at the two endpoints of this edge E, let me call them U and V, the spanning tree has to contain a path from U to V. Now this path starts at a white vertex and ends at an orange vertex. So somewhere in the middle, it has to have an edge with one white endpoint and one orange endpoint. In fact, this path has several such edges. I'm just going to pick one arbitrarily and call it E prime. Okay? So, I'm mostly picking this one because it's horizontal, not for any particular reason. Yes? Orange are the vertices in S. S. Arbitrary subset of the vertices. E, this dashed edge, is the lightest edge in the whole graph that has one orange endpoint and one white endpoint.
Okay, but you're not saying that if you add E,
no, I'm not saying that. I'm not saying that, at least not yet. Okay, so is everybody clear on the definitions of, S is are the orange vertices, E is the lightest edge that has one orange endpoint and one non-orange endpoint. T is some spanning tree that doesn't contain E. And then E prime is some other edge on the path between the endpoints of E that has one orange endpoint and one white endpoint. Doesn't matter which one. Okay? Now, one thing that we know just from the definitions, E, by definition, is the edge of minimum weight that has one orange endpoint and one white endpoint. E prime is another edge that has one white endpoint and one orange endpoint. And so, by definition, the weight of E prime has to be bigger than the weight of E. Right? That's what the definition, how I defined E. Okay? Now, watch what happens now. If I delete E prime from the spanning tree, the spanning tree falls apart. It now turns into a forest that has two components. And because the spanning tree doesn't have any, this is because the spanning tree doesn't have any cycles. If you delete E prime and the resulting graph still hung together, that would mean there's more than one path between those 2 points that would give you a cycle, and that's not a tree. So in particular, one of the components of T minus E prime contains U, and one of the components of T minus E prime contains V. So now if I add E to this forest, now I get another spanning tree. Okay? So T minus E prime plus E is a spanning tree. But what happened to the weight of the spanning tree when I went from T to this new spanning tree? Let me just call this T prime. I decreased the weight by W of E prime, and then I increased the weight by W of E. Right? So this means that the total weight of T prime is bigger than the total weight of T. Sorry. Sometimes I could swear this is my right hand. Right? By doing this exchange, I've replaced a heavier edge with a lighter edge. And so I've ended up with a lighter tree. Right? So what I can conclude from this is T is not the minimum spanning tree. Okay? Yes? Because I started with let S be an arbitrary subset of V. That's what the orange nodes are, is the first line of the proof.
Okay, but if you remove
here?
Yeah. So that's an edge between an orange and a
But it's not the lightest edge between the orange and the white node. I put it here. Remember, this is an illustration to give you intuition. The picture is not the proof. I chose an example. I chose an example that had these 7 orange nodes, and the lightest edge between orange and white was up at the top. Why is it that way? Because I wanted a picture that would look nice, not because there's has any particular value in the proof. So yes, it could be that this edge is the lightest edge between orange and white. But then it's already inside the spanning tree, and so I wouldn't have actually chosen that spanning tree. right? Right, the real proof is the logic. Pick your favorite subset S, that identifies a particular edge E. Pick your favorite tree that excludes E, that is not the minimum spanning tree. Yes?
Is there any chance that there's just one edge coming from orange and edge white?
Yes, it is possible. In which case, that edge must be in every spanning tree. Because there must be a path in the spanning tree from some orange stuff to some white stuff. And so if there's only one orange-white edge, that edge has to be on that path, and so it has to be in the spanning tree. So if there's only one edge crossing that boundary between orange and white, it's in every spanning tree, and therefore it's in the minimum spanning tree. Okay. All right, so the punchline is, by doing this exchange argument, T is not the minimum spanning tree. And that ends the proof. Okay. If it's the minimum spanning tree, it includes the lightest edge leaving S. That's the same as if it excludes the lightest edge leaving S, then it's not the minimum spanning tree. Okay, so this is the proof of correctness. This is why every minimum spanning tree algorithm works. Because I only ever add safe edges to F. There's a even easier proof. Why can I throw away useless edges? Right, so here I've built up my F for a while, and I noticed that there's some useless edge over here. Why can I throw that away? Because I know I'm never going to add it to F, because adding it to F would create a cycle, QED. Okay. So then the only thing I have left to do is to figure out how to identify safe edges, what order to add these safe edges in, how to identify useless edges if I want to do that, what order do I throw them away? So can someone suggest a strategy for this? I'm allowed to identify any safe edge I want. In fact, someone already has suggested a strategy. Yeah?
Just pick an arbitrary node and then select that.
Huh?
That would be the safe edge for that node.
Right. And then, that's step one.
And then add it to the minimum.
Add it to the minimum spanning tree, and then how do you find the second safe edge? I want a general strategy, not just the first iteration.
The node that you just connected to?
So there are a couple of different ways that one can do this. Okay. What you're suggesting is Prim's algorithm, which was discovered by Yarnik first. So of course it's called Prim's algorithm. Yeah. Did you have a question? Okay, so let me talk about this one first, and then I'll come back to you. Okay, grow one component of F. A single vertex. Okay, so I'm going to anoint one of the vertices as special. And I'm going to, therefore, whatever component of F contains that, special node is the only component of F that I care about. Find the lightest edge leaving my favorite component of F, add it to F, recurse. So what you end up doing in this case is growing the spanning tree one edge at a time. Okay? This, in fact, is the same as whatever for search, where the bag is a priority queue, and the priority of an edge in the priority queue is the weight of that edge. So you already know how to implement this. You know how to implement whatever for search. Now I tell you, okay, the bag, it's a priority queue. You're given the priority as part of the input. You know how to build a heap. You're done. It's correct because I'm only ever adding safe edges to F, and I just proved that that works. It's fast because you know you're just doing whatever for search, but at each step you're doing some priority queue operations. Okay? So in the end, this algorithm is going to run in, assuming the graph is connected, something like E log V time.
So I don't know. There's like another edge that leads to it. That's just from a single node, like by itself. It only has one edge that leads to that node.
Well, what if it isn't? What if there isn't another isolated node that has an edge leading to your favorite node? I mean, if there is, then great, you can add it. And if there isn't, your algorithm has to do something. Right? So I need a general strategy of identifying a safe edge. Right? So the way that I'm doing it, I'm just picking a favorite component and saying, add the lightest edge leaving that component. Right? So this grows the spanning tree out from the seed vertex, and that's it.
Sorry.
Okay? So there was another suggestion in the back.
I think you could just pick the lightest.
Okay, so, and that gives you the first safe edge. The lightest edge in the entire graph is in particular a safe edge for its two endpoints. But then how do you pick the next safe edge? Again, I need a general strategy that I jump in the middle of the algorithm. Yeah. In the back. Yeah.
Then you check to see if the next.
Okay, so where we're headed here is Costco's algorithm, which is probably the one that you implemented, if you've implemented one of these. Look at the edges in increasing order of weight. If an edge is safe, if an edge is useless, ignore it. Else, it's safe. Add it. Okay, so I'm looking at the edges starting at the lightest edge and moving up in increasing order of weight. If an edge joins this has both endpoints in the same component of F, by definition it's useless and I can throw it away. If it has one endpoint in one component of F and another endpoint in a different component of F, it must be the lightest such edge, because if it weren't, I would have already added some other edge connecting those two components. Right? So this lets me look at the edges in the right order so that whenever I look at an edge, I can tell immediately, in principle, either it's useless or it's safe. Now that's not true in general. Right? So in general, in the sort of generic strategy, one of these dashed edges is safe, and the rest of them are neither safe nor useless. I don't know what to do with them yet. But if I consider all of the edges in increasing order, then whenever I look at an edge, if it's still connecting two different parts of F, it must be the lightest edge connecting those two different parts of F. It must be safe. Now, making this actually work quickly requires a little bit more effort, because I need a data structure that will allow me to tell quickly, hey, here are two vertices, are they in the same component of F? Now, in 225, did you see disjoint set data structures, union find, path compression, that sort of thing? That's exactly where you would use that. Okay? So the running time is basically going to be dominated by sorting the edges, because I need to look at them in increasing order. And then I need to do E union find operations. And if I implement up trees with union by rank and path compression, see Wikipedia or see my notes if you don't know what that means, what you're going to end up with is this bizarre-looking running time for the second phase of the algorithm. It's the number of edges times the inverse Ackermann function of the number of edges. For all practical purposes, the inverse Ackermann function is 5. The actual definition is a bit complicated, and in the interest of time, I should probably skip it. But it's less than log E, it's less than log log E, it's less than log 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 E. It's less than the number of times you have to take the log of E to get down to 1. That's log star of E. It's less than log star star of E, which is the number of times you have to take log star. Right? In fact, the right definition of alpha is how many stars you need before the result is less than 2. It's small, right? But it's not constant. It's only constant in practice. Or outside of this room, it's a constant. Inside of this room, it wants to be a constant, but it doesn't quite make it. Okay, so in any case, the sorting is going to dominate this, and so you're going to end up with roughly the same running time as Yarnick's algorithm. Okay, those are the algorithms you've seen. I'm going to show you an algorithm you haven't, I think. This was the first algorithm. So Boru was a telecommunications worker in I believe it was Czechoslovakia in the 1920s. And he was faced with the problem of trying to connect various telegraph stations in what is now the Czech Republic using the minimum amount of wire. Hey, it's a minimum spanning tree problem, right? You have a graph where the cities are the nodes, and you have the amount of wire that you need to connect those two nodes is the weight of that edge. And so he published this paper in 1926, which described, in fact, not only an algorithm to do this, but a parallel algorithm to do this. And this is really remarkable given that there were no computers for another 3 decades. The standard nomenclature for graphs, not graph algorithms, for graphs, was not really established until the 1940s and 1950s. The graphs are old, but the vertices, edges, paths, spanning trees, those phrases were really not standardized until many years after this. And so when you read this paper, assuming you can read it in Czech, if you read an English translation of this paper, it reads very strangely. And this is one of the reasons why this algorithm didn't make it into any of the textbooks. The other reason it didn't make it into any of the textbooks is because it wasn't in any of the textbooks. It's not in CLRS because it wasn't in Aho, Hopcroft, and Ullman because it wasn't in Knuth. But the interesting thing is, Costco knew about it. And the reason he developed his algorithm is he thought Boruvka's algorithm was too complicated, partly because it was perhaps written in Czech. And then once Costco in the 1950s knew about it, but nobody else could see the original paper because it was on the other side of the Iron Curtain. And so people forgot about it for a while. So here's Boruvka's algorithm. Find all the edges that are safe, add them. If the F is connected, you're done. If not, recurse. Find all the safe edges and add them. Now, you could reasonably ask, well, great, this is a nice, simple sounding algorithm, but how do you actually do it? And just to give you an idea of how the algorithm would actually execute, Good, some of you still get that joke. Her book just came out, by the way. Go buy it. It's cool. So here's the example graph that I showed you before. At the very beginning, I could just say every vertex, find your lightest edge leaving you. Everybody point at your best friend. Okay? And then if there's any edge that has at least one arrow pointing along it, you'll add to your forest. Okay, now it turned out in this particular case, I almost had a spanning tree. I mean, I only have 2 components left. And so each of those components points along its lightest outgoing edge, and because there are only 2 components, this is actually the lightest edge in the graph that isn't useless. So both of the components pick it, and then I'm done. Okay? So there are 2 things that I need to nail down in order to turn this sketch into a real algorithm. One, how do you identify all of the safe edges? Adding them to the forest is relatively simple. And second, how many phases is this algorithm going to go through? Okay, so let me attack these one at a time. Right? So the question is, how do I do this? And the next question is, how many times do I need to do that? Okay? So let me start with the first one. All right, so I'm going to draw edges in, let me see if I can find the gray marker. If I find something lighter. Okay, here. These light edges are not necessarily in the minimum spanning tree. These are just edges in the graph. And I'm in the middle of running the algorithm. Okay. And now my forest in the middle of the algorithm looks something like, this. Okay? Now, for each of those 3 components, I want to find the safe edge leaving that component. So I'm going to identify at most 3 edges, and in fact, at most 2, because one edge is always going to be identified twice. So, how might I do this? Well, one thing that I need is I need an ability to look at an edge and decide, among other things, whether the edge is useless. I need to be able to look at the edge and decide which 2 components does this edge connect. Right? Because each component, you can imagine, is going to keep track of all the edges that touch it and maintain the lightest one it's seen so far. But then I need some way to say, look at every edge, and okay, suppose that edge touches components I and j. If it's lighter than the lightest edge I've seen for component I so far, update on component I. If it's lighter than the lightest edge I've seen touching component j so far, update the lightest edge for component j. And then at the end, each component will know what its safe edge is. Right? But first, I need a way of identifying quickly which components a particular edge touches. This is, well, let me ask, can anybody think of a way to do this? I'm starting from scratch now. I'm just given a graph, find safe edges. Yeah?
Do you sort of what we did for the other algorithm?
Yes, you can do that. Every time you, in fact, what you can do is every time you add an edge, you just say union, okay? And then as you scan through the edge, scan through the list of edges, you can say, Okay, here's an edge UV. Find U, find V. Are they different? Are they the same? If they're different, then in fact, find will return an identifier for that set, that component, and you can keep track of those. Doing the analysis of that particular version of Boru's algorithm is a little bit more complicated. It works brilliantly in practice. It will run in the end in linear time. But seeing that it runs in linear time, and in particular seeing why that alpha doesn't come in, is a little bit tricky. So there's something simpler. There's something that we've already seen. Well, so one thing that I might think of as a way to do this is if there was some way to magically label each of the vertices with some number that represents its component. So I'm going to label all the vertices in component 1 with a 1. And I'm going to label all the vertices with component 2 with a 2. And I'm going to label all the vertices in component 3 with a 3. And now when I look at an edge, when I say I look at this edge here in the middle, I look at its endpoints and say, oh, you're in component 1 and you're in component 2. Maybe this is the safe edge for component 1. Maybe this is the safe edge for component 2. As opposed to this edge, where I say, oh, you're in component 1 and you're in component 1. Ah, this is useless. Throw it away. Okay, so if I could compute this numbering, then I could tell in constant time whether an edge is useless or not, and possibly whether it's safe or not. But how do I compute this numbering? Where did it go? I had a list of things that we'd actually seen before. Try again. How do we compute that numbering? Yes? Yeah?
Actually, I have a question.
Okay, sure.
I feel like disjoint sets are the perfect structure.
Okay, so there are two solutions here. One of them, you maintain a disjoint set data structure and you maintain this information. I'm proposing that we do something simpler that's easier to analyze. We don't maintain anything. We start with a bare graph with those edges, and we need to compute this labeling, and then we need to scan and compute all the safe edges. Yeah? It's not a directed graph, but you're close.
I don't know, I was just going to say like number.
You're maintaining information. I literally want to jump into the middle of the algorithm. Hey, somebody was running Boru's algorithm and they fell asleep. Here's F. Find all the safe edges. I claim you can still do this in linear time. No alphas, no data structures.
Right, but you just like keep the number right.
No, I'm not allowed to keep anything. The guy who was running the algorithm fell asleep. He dropped his hard disk containing all the data structures in the toilet. It's just not going to happen. You got to start over. How do you number the components of a graph? Yep, right here. The first algorithm we saw. Right, so I run a whatever for search in F. I start here, well, maybe here. I start here, 1. I'm going to number everything connected to this vertex with a 1. Okay, whatever for search, I find all of these things, and whenever I visit a vertex, I label it with a 1. And then in a wrapper function, I say, oh, let me just do a for loop over all the vertices, and if I see a vertex that hasn't been marked yet, I'm going to increment my counter for how many components there are and label the next component with that number. Right? So with whatever for search, I can label the components. Right? And then for every edge in the graph, I can now look up in constant time whether the two endpoints are in the same component. And if they're not, then I can say, hey, component on the left, am I better than the edge you've seen before? Component on the left, am I better than the edge you've seen before? And so in the end, you get an algorithm that looks like this. Okay, so here's the main wrapper function. Count and label is a subroutine that uses whatever for search to count the number of components in F and label each vertex in F with a number that corresponds to its component. Okay? I believe Sin was actually supposed to describe that algorithm on Tuesday. If not, it is in the lecture notes. Okay? It's really just DFS with a for loop around it. Okay? And then as long as the forest has more than one component, I add all the safe edges, and then I recurse, which means I recompute this labeling, I recount the number of components, and I relabel the vertices, and then repeat the loop. Add all the safe edges, and right? And then recurse. Once the count is equal to 1, that means F is connected, and I'm done. So this line here is whatever for search, which you already know how to implement. Okay? And in fact, you already know runs in linear time, vertices plus edges. Then the second part of the algorithm is really just a bunch of bookkeeping. Okay, so I'm going to keep an array S. S sub I is going to eventually be the safe edge leaving component I. And I look at every edge. Its label is the number, which component the vertex is in. If the two labels are different, then maybe this is the safe edge leaving the component containing U. Maybe this is the safe edge leaving the component containing V. And so I just compare, hey, is this edge lighter than what I currently think the safe edge is for that component? If it is, I update the safe edge, right? And then here, I'm doing all of the adding. Right, here, I'm finding all the safe edges. Right, so in the first for loop, I find all the safe edges just by brute force. Look at every edge, see if it's safe. And in the second for loop, I add it to F. No up trees, no path compression, no pointer chasing other than whatever you need for whatever for search, just brute force. Okay? The running time of this algorithm on the screen currently is dominated by the big loop for each edge. It's just going to be order E. It's proportional to the number of edges. Right? So this algorithm is going to run in order E time. I believe you could implement this now. Certainly you could implement this part of Boru's algorithm in about 10 minutes. Right? You need an implementation of depth first search. Okay, that'll take you another 20 minutes. And then once you've done that, you've got the wrapper function that makes it all work. No data structures, no inverse Ackermann, no amortized analysis, no path compression, no dynamic memory management, just brute force. Okay? So the answer to the first question, then, is essentially whatever for search plus scan the edges, right? And it's all going to take linear time and the number of edges. So the second question is, how many times do I have to do this? Okay. So I'm going to imagine for the moment, let's just think about the first iteration of Boru's algorithm. Okay, I'm going to start off with V components, one for every vertex. In fact, each vertex is a component by itself. Okay, then every vertex is going to point to some other vertex. Okay? Everybody's going to pick the vertex that it likes the most. Yeah. Yeah. In the end, it's going to be log E. Yeah, well, in the worst case, what's going to happen is they're going to join up in pairs. Okay? But in the general case, what happens is everybody points to each other, and now I need to add in some edges into my forest. So as long as there's at least one arrow going along my along an edge, I'm going to add that to F. Okay? So how many edges am I going to add? Well, I have V arrows. And then, so you might think I'm going to add V edges, but that's clearly too many because I can't have V edges in a minimum spanning tree. But there's some edges that get added twice, in effect. There's some edges that have both arrows. Minus some number, let's call it D, edges with 2 arrows. Okay? Now, how many edges can there be with 2 arrows? What's the largest number of edges I can have with 2 arrows? V over 2, because I have V arrows. I put 2 of them here, I put 2 of them there, I put 2 of them there. They're only V over 2, right, there are V over 2 edges at most that are going to have 2, maybe less, right? So in the end, I'm going to add at least V over 2 safe edges. Okay? Now, after I've added those safe edges, every time I added a safe edge, the number of components in F goes down by 1. All right? So after I add these safe edges, I have at most V over 2 components in F. Right? So after I add the safe edges, the very first iteration, I've reduced the number of components from V to at most V over 2. And in fact, this argument works more generally. Right? Now, if I'm in the middle of the algorithm, the number of arrows that I'm going to add is, however many components there are in F. And so the number of edges that I'm going to add is going to be at least half of that, which means every iteration is going to reduce the number of components in F by at least half, by at least a factor of 2. Okay, started out with 1,000. After one iteration, I have at most 500. After another iteration, I have at most 250. After another iteration, I have at most 125, and so on. So after log V iterations, the algorithm is done. The number of components of F has been reduced to 1. That's more or less the definition of log. Okay? So log V. So that means the overall running time is E log V. Okay. I want to beg your indulgence for 1 minute, explain why I think this algorithm is better than the other ones, even though the running time looks the same. 3 reasons. 1, maybe the number of components will go down faster than that. So this is the worst case running time. In actual practice, you end up dividing quite a bit faster than a factor of 2 at every iteration. 2, so the other algorithms, the analysis is tight for every graph. 2, the algorithm can essentially be parallelized. Every component can be run on its own independent thread to figure out what its safe edge is. Which means, in particular, if you're running on a multi-core machine, you can send different vertices off to each core, and they can run independently. Costco's algorithm and Prim's algorithm look at things in a particular order. And that makes them intrinsically serial. 3, there are faster minimum spanning tree algorithms. They're all based on Borufka, not on the other 2. So if you're only going to remember one minimum spanning tree algorithm, remember this one. And if you're ever going to teach one minimum spanning tree algorithm. Teach this one. Okay, thanks, and I'll see you on Tuesday.